Welcome back to RaWMachines, the journey exploring the most impressive processes across the globe. Today we will discover how massive ships weighing hundreds of thousands of tons are lifted out of the water for repair, maintenance, and upgrades in modern shipyards. Behind this seemingly impossible process are giant dry docks, complex engineering technology, and the precise coordination of hundreds of skilled engineers and workers. Let's get started. If the ocean is where giant ships are born to operate, then the dry dock is where they are cared for and restored after long voyages. Viewed from above, a dry dock looks like a colossal basin constructed of reinforced concrete. Some docks stretch up to 400 meters long and dozens of meters wide, large enough to accommodate the world's biggest container ships. The unique feature of this structure lies in its ability to precisely control water. When receiving a ship, the dry dock is flooded, turning it into a tranquil pool that almost merges with the surrounding harbor waters. But when the repair process begins, all that water is drained by extremely powerful industrial pumping systems. After just a few hours, a space that once held tens of thousands of cubic meters of water becomes completely dry, revealing the ship's hull, a part very few people ever get to see. Massive steel plates, faded anti-fouling paint, and countless marine organisms clinging to the hull are now clearly exposed. To the ocean, this is merely a natural ecosystem, but for the maritime industry, this biofouling is a serious problem. Therefore, the first step in the maintenance process is usually cleaning the entire hull. The most common method for this task is known as hydroblasting, which involves cleaning with ultra-high pressure water jets. Instead of using chemicals or mechanical scraping tools, this system sprays ultra-high pressure water jets powerful enough to strip away the moss and marine organisms tightly bonded to the ship's steel surface. Workers move along the hull, cleaning every section from the bow, along both sides of the ship, all the way to the stern, where the propeller and rudder are located. Compared to scraping or grinding methods, high-pressure water jets can remove the buildup while leaving the steel surface and protective paint layers intact. As a result, the ship operates more efficiently, and engineers can more clearly observe the actual condition of the hull. However, this remains a grueling task. Workers often must stand on scaffolding dozens of meters high, or work on the sloped surfaces of the massive hull in wet and slippery environments. For this reason, in recent years, the ship repair industry has begun using a new technological solution: hull cleaning robots. One of the most prominent devices is the RM6 magnetic crawler. The RM6 is equipped with cleaning systems similar to those used by human workers, including high-pressure water nozzles and industrial brushes. As the robot moves, powerful water jets sweep across the steel surface, stripping away moss, barnacles, and long-standing residue from the hull. One major advantage of this system is its flexibility in various conditions. The robot can operate while the ship is in dry dock, but it can also function while the vessel is still afloat. In some cases, it can even work underwater, cleaning areas that are difficult for humans to access. By utilizing robots, many dangerous tasks for workers are significantly reduced. Simultaneously, the cleaning process becomes faster and more consistent. However, cleaning the hull is only the first step. Once the surface has been inspected and prepared, Many critical components of the ship will be disassembled, repaired, or replaced. One of the most vital systems requiring periodic inspection is the bow thruster. This device generates lateral thrust, allowing the vessel to move sideways or pivot precisely when navigating ports, canals, or areas with limited space. In a typical repair project, the vessel Max Venture had its entire bow thruster system replaced by the BMT Repairs technical team. This process began with the disassembly of the old equipment. Engineers disconnected the electrical, hydraulic, and control systems before using heavy-duty cranes to lift the old unit out of the hull. Next, the installation area was prepared. A new support structure was welded and reinforced to ensure the new thruster could operate stably under heavy load conditions. Once everything was ready, the new equipment was maneuvered into position by crane and carefully installed into the thruster tunnel. Finally, the engineers reconnected all electrical and hydraulic systems, followed by a trial run to ensure the equipment functioned correctly. With the bow thruster restored, the ship regained the maneuverability essential for navigating safely within the tight confines of a seaport. This is one of many examples showing that ship repair is sometimes like a massive surgical operation, where components weighing several tons are removed, replaced, and reassembled with near absolute precision. The video also introduces the modification process of the Hamburg-Süd container ship, Santa Rita, in Rotterdam. The first stage involves a 3D scan of the stern area to precisely determine the surface geometry, ensuring that the installation of the twisted fins achieves high accuracy. This is a pivotal step as it helps the system operate efficiently and maximizes energy-saving potential. Once the scanning is complete, the Becker twisted fins are brought in for adjustment according to the ship's specific configuration. This process includes trimming and calibration to ensure the fins achieve the exact required size and shape. Once the components of the Becker Mewis duct twisted system are prepared, the next step is the precise adjustment and positioning of the flow-directing fins on the ship's stern. First, technicians carry out a process called fin tailoring. Based on the measurement data and the 3D model of the hull, the steel fins are trimmed and modified to fit the actual structure of the stern perfectly. Deviations of even a few millimeters can negatively impact flow efficiency. Once the fins are finalized, they are moved into place for final positioning. Engineers utilize specialized measuring equipment to ensure each fin sits at the exact angle and distance specified in the design. Once the flow-directing fins are accurately positioned, the next step is to permanently weld them to the hull. Engineers inspect the surface conditions and metal temperature using specialized measuring devices, sometimes even utilizing infrared scanning to ensure the welding area meets the necessary technical requirements. Next, the fins are welded to the hull using advanced welding methods, ensuring both precision and high durability for the structure. This task requires a high level of professional skill to achieve the desired technical quality. Upon completion, the welds are thoroughly inspected using magnetic particle testing and ultrasonic testing to ensure there are no defects. Thanks to this improvement, the ship can save approximately 3% of energy during its operation. The Becker flap rudder is a critical component of high-performance propulsion systems, enhancing a vessel's maneuverability and control during operation. Below is its operating principle across various operational scenarios. One of the standout advantages of this system is its ability to improve the ship's turning circle. As the rudder rotates, the rear flap amplifies the force of the water flow, enabling the vessel to turn more quickly and reducing its turning radius. This is particularly crucial for large-scale vessels, which typically face difficulties when maneuvering in confined spaces. In addition to superior turning capabilities, the Becker flap rudder helps the ship maintain a stable heading in extreme weather conditions. When facing heavy swells or strong winds, the flap can be adjusted to generate balancing force, allowing the captain to maintain a precise course without the need for constant corrections. In emergency situations, this system demonstrates its value even more clearly. Because the flap can rotate independently, the rudder is capable of generating a much larger turning force in a shorter amount of time. This allows the vessel to react rapidly to avoid collisions with other ships, or to bypass unexpected obstacles in the water. This maneuverability is particularly useful when the ship operates in seaports or narrow canal routes. In areas where maneuvering space is restricted, the Becker flap rudder allows the vessel to execute turns with much greater precision and flexibility compared to traditional rudder designs. A prime example of this technology's application is the rudder upgrade project for the cruise ship MS Amera, carried out by Becker Marine Systems. The project spanned approximately 6 months, encompassing the entire design, manufacturing, and installation process of the new rudder, without requiring any structural changes to the existing shipyard facilities. Originally, the vessel utilized a semi-spade rudder, a type of semi-suspended rudder common on many ships built in the last century. However, this design has limitations in maneuvering efficiency for modern, large-scale cruise ships. To improve maneuverability, the Becker flap rudder was selected as the new system. This design consists of a main rudder blade and a trailing edge flap that can move independently, increasing steering force and providing a faster response when the ship changes course. A major challenge of the project stemmed from the fact that the ship's original design blueprints dated back to the 1970s. These drawings were hand-drawn and lacked many detailed technical specifications, making the installation of new components significantly more complex. Therefore, Becker Marine Systems conducted multiple inspection and measurement steps to ensure every component achieved the necessary precision before installation. Engineers worked continuously, cross-checking each other's data to guarantee that every detail met rigorous safety standards. After the main components are prepared, the rudder trunk is treated and protected with an anti-corrosion coating. The thickness of the coating is controlled in micrometers, with each layer being approximately 250 micrometers thick. At the same time, engineers finalize the technical documentation and install the bearings for the system. The shaft tube acts as the connection point between the ship's hull and the steering gear, so the structural area at the stern must be precisely reinforced before installing the subsequent components. Once the preparations are complete, the technical team begins installing the new rudder stock. This process is carried out in careful, sequential steps, starting with the starboard side shaft, and followed by the installation of the steering gear, the system that controls the rudder. One of the most critical steps is aligning the rudder stock in the neutral position. Engineers must ensure the shaft is perfectly straight and devoid of any misalignment. Within a ship's steering system, even a very minor deviation can cause mechanical wear or diminish steering efficiency. After the rudder stock is aligned, the engineers proceed to install the main rudder blade, with each unit weighing several tons. This work demands intense concentration due to the confined space in the workshop, and the fact that many technical teams are working simultaneously. The components are secured with massive nuts weighing hundreds of kilograms, tightened using industrial-grade torque wrenches. Afterward, the flap is attached to the rear of the main blade to complete the Becker flap rudder structure. Finally, the system is verified using a push-up test, a hydraulic pressure test designed to confirm the structural integrity of the connection between the rudder stock and the rudder blade. Once the welding and assembly are complete, the ship enters the operational testing phase while still in dry dock. Before testing begins, the area around the rudder is inspected for safety to ensure there are no obstructions. Electrical engineers then activate the steering gear system and conduct a swing test, which involves rotating the rudder through various angles. This test confirms that the entire system responds accurately and operates smoothly. Once the results are satisfactory, the access covers are welded shut, and the final coat of paint is applied to the metal surfaces, marking the completion of the work in the dry dock. After months of continuous work, the new rudder system is finally complete. The ship leaves the dry dock and enters the sea trial phase, which lasts for approximately 3 days. During these trials, the captain evaluates the maneuverability and responsiveness of the new rudder system. Becker technology has been in use for over 70 years across various types of vessels, and the test results confirm that it provides highly precise control. As the MS Amera leaves the port of Hamburg and begins its new journey, the 6-month renovation project is officially complete. The ship now possesses superior maneuverability, operates more efficiently, and meets modern technical standards. Beyond the hull, another critical component that requires regular cleaning is the propeller. To perform this task, engineers use a specialized device called a cavit cleaner. This device operates based on the phenomenon of cavitation, creating cavitation bubbles around the propeller. When these bubbles collapse, they generate tiny but extremely powerful forces, sufficient to dislodge sludge, marine growth, and debris adhering to the metal surface. During operation, the cabot cleaner is attached directly to a diver. The diver then maneuvers the device around the propeller blades, allowing for the cleaning of the entire area without the need to bring the ship into dry dock. This method enables fast and effective propeller cleaning while keeping the metal surface smooth. As a result, the propeller's propulsion efficiency is improved, fuel consumption is reduced, and various operational issues can be prevented early on. Most importantly, maintenance can be performed right at the port, saving significant time and costs. In the offshore oil and gas industry, many pipeline systems must operate continuously for years on the sea floor. When damage occurs, halting the flow for repairs can cause severe disruptions to entire extraction operations. Consequently, a specialized solution is utilized: hyperbaric repair. This method allows engineers to conduct repairs directly on active pipelines without stopping the internal flow. The primary goal is to restore the structural integrity of the pipe while maintaining the continuous operation of the offshore oil or gas transport system. However, this is one of the most complex engineering tasks in the offshore industry. Every action must be performed under high pressure and within a confined workspace, requiring rigorous safety controls. Before repairs begin, engineers conduct a detailed assessment of the pipeline's condition. They survey the geometry of the damaged area, measure the wall thickness, and analyze operational parameters such as internal pressure and temperature. A critical step in the preparation phase is the installation of suction piles on the seabed. These structures serve as the foundation to anchor the hyperbaric working environment.
It's Mediterranean chicken, chipolata sausage, okie dokie.
Behind us, we can use to heat the pipe to the required.
Once the foundation is ready, the hyperbaric habitat is lowered to the seabed using a hydraulic system. The habitat is positioned directly over the damaged pipeline section and aligned with the suction pile system. Once secured in place, the next step is to create a dry working environment inside the structure. Seawater is evacuated from the habitat step by step, while the pressure is carefully controlled to avoid affecting the active pipeline. The result is a dry, high-pressure workspace that allows engineers to perform repair tasks directly on the pipe.
We got measurement of 81.5.
This is the pipeline, so it's the same pipe as in Indonesia. And this is also the incline line. We're going to find it in Indonesia.
Once the working environment has been established, the technical team begins the installation of the standoff sleeve. This structure is positioned around the damaged area to restore the pipeline's mechanical strength and provide a stable surface for the welding process.
On each individual layer, and that's basically the surface preparation and the quality control after application. Yeah, I'm not sure. Fast.
The sleeve must be concentrically aligned with the main pipeline to ensure it can withstand the system's operational stresses. Afterward, the welders perform hyperbaric welding. This is a specialized welding process designed for high-pressure environments. The objective is to ensure the weld possesses metallurgical stability and sufficient long-term load-bearing capacity under offshore operating conditions. After each welding stage, engineers conduct quality assurance using non-destructive testing, NDT methods. The two most common techniques utilized are ultrasonic testing and radiographic testing. These methods allow for the assessment of weld penetration, the detection of internal defects, and the verification of the overall quality of the metallic bond. Throughout the construction process, the hyperbaric habitat is adjusted and re-secured as necessary to ensure a stable position on the suction piles. Once a stage is completed, the divers return to the hyperbaric environment to continue welding the subsequent sleeve sections, following the same rigorous technical procedures. Once the welding process is complete, the repaired area is coated with an anti-corrosion protective layer to shield the metal from the long-term effects of the marine environment. In certain cases, components of a cathodic protection system are also installed. This system helps prevent electrochemical corrosion, extending the operational lifespan of the pipeline following the repair. Once all technical phases are completed, a final round of inspections is conducted to confirm that every engineering standard has been met. When all inspections pass the required benchmarks, the hyperbaric environment is decommissioned and removed from the construction site. The pipeline is then returned to its normal operating state, continuing its mission of transporting products across the seafloor. Now, we will move on to the next procedure, cleaning the cargo holds for a grain-carrying vessel. First, the technical team identifies potential hazards such as sharp edges, blind spots, or confined spaces within the cargo hold. Then, a safety system is established, including access equipment, fall protection, ventilation, and communication systems. Cleaning is typically performed using high-pressure water jets, starting from the upper section of the hold and moving gradually downward. This method helps avoid recontaminating areas that have already been cleaned. Due to the complex structure of the cargo hold, many areas can accumulate grain residue, moisture, or rust. Locations such as structural corners, frames, and internal piping often require particularly thorough inspection. Throughout the cleaning process, the drainage system is continuously monitored to prevent water accumulation in the cargo hold, which could reduce cleaning efficiency. Upon completion, the cargo hold undergoes a full visual inspection. To meet grain carrying standards, the internal surfaces must be free of previous cargo residue, loose rust, paint scales, and standing water. This cleaning procedure not only protects the quality of the cargo, but also contributes to the preservation of the ship's internal structure. Throughout the journey we have just followed, we have witnessed a vast world of engineering behind the massive ships quietly moving across the ocean. Each step in the process is a combination of human experience and high-tech engineering. Magnetic robots clinging to hulls to clean off marine growth, giant hydraulic systems lifting and installing components weighing tons, or hyperbaric welding techniques performed deep on the ocean floor, all reflect the continuous advancement of maritime engineering. Behind these hundreds of meters-long ships are hundreds of people working continuously day and night. Engineers calculate every millimeter, welders perfect every metal joint, and technical teams inspect every system to ensure everything functions perfectly before the vessel returns to the open sea. Renovation projects such as replacing rudder systems, upgrading energy-saving equipment, or repairing offshore pipelines showed that the maritime industry is about more than just transport. It is a massive engineering sector where each ship is a complex mechanical system that must be continuously maintained, upgraded, and perfected throughout its life cycle. From underwater propeller cleaning and pipeline repair in hyperbaric environments to hull surface preparation and cargo hold cleaning according to international standards. All are silent tasks that play an essential role in keeping the world's shipping lanes running smoothly. Because every day, thousands of ships are still moving across the oceans, carrying the fuel, raw materials, and goods that feed the global economy. And behind every such safe voyage is a massive network of engineers, workers, and technology working silently to keep these giant steel machines in peak condition. That is the story of processes rarely seen, yet they are the foundation that keeps the modern world in motion. Thank you for listening to the end of the story. If you enjoyed videos like this, please like, share, and subscribe to the channel so you don't miss our next stories. RaWMachines says goodbye and see you again soon.